easier to figure out what the answer is. I'll just say that as my first piece of advice when you're thinking about your research project. Don't just collect data. Data means nothing if you have no question. So the question comes first. If you have the question, then we can figure out how to analyze it. Well, good morning, everybody. Hope you're all doing well. I think this is, I know the last time I did this was one of the first ones that we did in this course, but you guys have seen several of these, I think, at this point, just sort of review lectures. And what Dr. Robertson has asked me to do today is to come in and talk to you guys about statistics and methods. Most of you probably have had my course either face-to-face or online before, and a lot of the material, it's not brand new, it's stuff that you've seen before. That's sort of the point of it being a review. So essentially what I'm going to try to do is cram a year's worth of material, a statistics course and a research course, into less than an hour and 15 minutes, preferably even less than an hour, so that we have some time to talk at the end about questions that you might have related to your own capstone projects. So I think you guys have slides. In fact, I see a copy of them out there, so I'll move pretty quickly through these things. But the point of today is to give you a general overview and hopefully remind you of some things you may have forgotten along the way. So just to give you a quick outline of what we're going to do, we're going to begin with the kind of a talk of statistics. What do we do that for? And of course, if you remember from our stats course a long time ago, the point of statistics is twofold. You want to describe data, and you also want to infer from data. So along that whole inference line, we then talk about z-scores and the normal distribution, and then we talk about hypothesis testing, and then particularly statistical tests that you would be interested in. And statistical tests I will not cover in particular because there are too many to fit into one simple lecture. But eventually, with your projects in this course, you'll have to do some sort of statistical test. I'm going to talk about what a statistical test is in general, what it tells you, and then once you pick the one that you're going to deal with, you can deal with the issues associated with that one at the time. And then we'll do a quick review of experimental as well as non-experimental designs, just so that you remember some of the vocabulary. One of the things about experimental design is it goes hand in hand with statistics. Certain experimental designs are analyzed in certain ways, and so if you're thinking about your capstone project and you say, I am going to do this within subject's 2-level factor, I mean, that's like, what is that? But it's extremely informative because it tells you exactly, oh, I need a paired samples t-test. Okay, so having that sort of design language is absolutely helpful for this. So let's get started. Statistics, why do we use them? Why do we make you take an entire course on it? As I mentioned, statistics as a field, at least as a service field to our discipline, breaks into two main areas. Descriptive statistics, where we use various statistics like mean, median, mode, standard deviation, variance, correlation, etc., to describe distributions. Right? We want to describe things, we want to simplify them, we want to organize them. That's all the function of descriptive statistics. And then there's the part of statistics which we call inferential, which in terms of our, if you remember from Psych 3330, is a bigger part of our course. In fact, I'm teaching it in the fall. This is week 6. In week 5, we began talking about inferential statistics. So easily 2/3 of the semester is spent talking about how we test claims about populations based on data gathered from samples. If you think about it, that's really what is key in doing any sort of statistics in psychology. We want to make claims as professionals, as researchers. We want to make claims about people in general. But we can't do that well because we can't test every possible person out there and every possible member of a certain population. And so what we have to do is we have to deal with the very limited sample that we get, and then use that sample and some statistics from that sample to infer about the greater population. And so inferential statistics, at its core, what we do is we answer the question that's in quotes. We ask ourselves, are the results that we're seeing above and beyond what we would expect from chance alone? And if so, then we make some kind of claim of there's a significant difference or something like that. What are distributions? Distributions are essentially the collections of data that we're interested in. There are many important distributions in psychology. We're going to talk about two in particular, the population as well as something related to samples. The population, of course, this is your collection of all possible scores of interest. You might be talking about the population of IQ scores. You might be talking about the population of running times for rats that have been exposed to a particular treatment in a water maze or something like that. There's all kinds of possible distributions that you could be talking about that would be called our population. Those are the things we don't know about. In order to find out things about them, we have to take things from a sample. Samples are the things that we deal with as researchers. These are the scores that you record from your participants. If you're doing a project where you're going to test 20 individuals on some semantic priming task, then those 20 individuals form your sample. And now we want to be able to use that sample to estimate this theoretical, untouchable, intangible population that we're actually interested in making claims about. So the sample is very important. In fact, it's so important that we have a distribution that befuddles students every semester. And I'm about to start befuddling students tomorrow in class. Look forward to that, Carissa. So we're going to be talking about distributions of sample distributions. What the heck is that? Okay. Well, the idea is if you are taking a sample, and let's say you want to compute a mean of the sample, you need to know how your sample mean compares to all the other possible sample means that you could have gotten. And so it's essentially a distribution of the action that you're doing over and over and over again, taking sample means. And if you collect all of those sample means together, turns out if your sample is big enough, those darn things turn out to be normal, which is why the normal distribution is one of our very important distributions that we study in this subject. So distributions are very important, and they form the core of what we're interested in statistics. So if these distributions are so important, how do we describe them? Well, we describe them mainly with two main characteristics. Now, if you get really funky and go to some other kinds of distributions, you'll need more than this. But for what we deal with on a daily basis, these two are usually good enough. We want to be able to describe the center, which could be anything like mean or median or even mode. The one that you pick for your data depends on the type of data that it is. Remember, you can't compute the mean of gender, all right? Even though every semester capstone students far and wide do. And I'll go to their poster and they'll say, well, our mean gender was 1.3, and I'll just say, explain that. What does that mean, right? I want you to think about that now, okay? I'm going to ask you what that means. And if you can't tell me what that means, you probably don't want to do it, okay? But you could compute a mode, right? Which gender occurred most often. The idea here is that mean, median, and mode are statistics. They are descriptors that really apply to specific types of data. And those kinds of things are in your old stats book, which I know you all have kept and can go back and look at, right? So center is an important descriptor. Also spread or variability. You want some measure of how spread out or how dispersed the data is. And so a common one that we use is standard deviation. If you remember what standard deviation is, once you get past stats and you start taking research, I just start saying, here, compute it in the computer. Then you get this number. What does it mean? What it means is, on average, how far the scores are from the mean. So for example, every time I give an exam and I'll come back and say the mean score was 72%, the standard deviation was 10.88, and I'm happy. I'm like, Dr. Fogger, why are you so happy about this? That's because of that standard deviation. That standard deviation of 10 points, thereabouts, means that on average, everyone differed from the center, and thus from each other, by 10 points. 10 points is a letter grade, right? So that standard deviation gives you an indication of not everyone scoring the same thing, that there is some natural dispersion. And so standard deviation is a good measure of that dispersion. So usually mean and standard deviation. Again, that depends on your data, but that's a really good set of descriptive statistics for any kind of measurement that you do. Just a visual here, when you've got distributions, low variability means low standard deviation. The scores are pretty similar to each other. You're going to have distributions that look pretty similar to this, right? They're kind of tightly packed around the center. But if you compare that to something like This one, which has a high variability, there's just a lot more dispersion through here. And so this one would have a bigger standard deviation than this one. Once we talk about mean and standard deviation, those two magical numbers provide a nice way for us to do lots of things that would be impossible otherwise. And the main thing that I want to talk about is the notion of a z-score. Okay? So z-score, as you know about, these are essentially, if you know the mean and standard deviation, you can take any data point, subtract the mean, so find the distance from the mean, and scale that or divide it by the standard deviation, and you get a z-score. The z-score is a way to make dissimilar distributions comparable. So if you want to talk about height and weight, those are on two different scales, okay? Height is on a scale of inches with certain numbers that you would expect. Weight is on a scale of pounds with other kinds of numbers that you would expect. And so you can't talk about, well, my height is bigger than your weight. What does that mean, right? You can't really compare those. That's a meaningless comparison. But if you were able to convert your height to a z-score and your weight to a z-score, then you can say, well, the z-score for my height is this, which means something, and the z-score for my weight is this, which means something. And those two numbers are now on the same scale and can be compared. Okay? So that's what brings up the whole idea of a z-distribution, which it turns out is everything that we base our stats techniques on. How does it work? Well, there's a formula that you might remember over here. Z equals x minus mu over sigma. Again, that just means you subtract the mean and divide by the standard deviation. The idea is that this gives me a number that has two components, size and direction. Okay? Direction is indicated by a positive or a negative. If I have a positive z-score, that you'll notice when I said positive, I couldn't help but keep from moving my hand to the right. A positive z-score means you're above the mean. All right? So if my daughter brings home a standardized test score and it's a z-score of plus 2.3, I'm really happy, right? Because it's above the mean, and then the size of it, 2.3, tells me, wow, she's 2.3 standard deviations above the mean. It literally uses the standard deviation as a measurement unit, as a yardstick. And so that z-score with those two components of direction and size gives me a lot of information, particularly about a data point relative to where it sits in the overall distribution. This data point is way over here in the tail, right? It's way up above the mean of 100. Or this data point is real close to the mean. I can get that just from the z-score itself. Okay, so remember, the z-score measures the number of standard deviations. You know, if you think about taking the MFT, the Major Field Achievement Test, you're probably not going to have to compute a bunch of z-scores, but it will be helpful to know what a z-score means. And a z-score means the number of standard deviations that you are from the mean. If you can remember nothing else, remember that. That is an absolutely crucial thing. Just to give a couple of quick examples of how they do work, let's suppose we've got a distribution here, and up here at the top I tell you that this is a normal distribution with a mean of 100 and a standard deviation of 50. Just made these numbers up, okay, just for some easy computations. Now what we want to do is take some values in this distribution and convert them to z-scores. So the first one that we'll do is we'll just say, well, what's 100, right? The 100 is the mean. What does the mean convert to when you transform it to a z-score? Well, one thing you can do is simply use the formula, right? The formula is you take the data point, x, subtract the mean, and then divide by the standard deviation. So if I do that here, I take the data point 100, subtract the mean 100, not much left there, is there? Divide by the standard deviation, that all turns out to be 0. What this tells you is an important principle of z-scores. A z-score of 0 means you are where? At the mean, right? And so that's exactly what that means. Let's say on the other hand, let's say you're at 150, right? So again, we'll do the same little technique. We'll plug 150 into this z-score formula. 150 minus 100 divided by 50. That top becomes 50, and 50 divided by 50 is 1. And moreover, it's a positive 1. And so because of that, we can say that 150 is 1 standard deviation above the mean, which we knew already because the standard deviation is how much? 50 points. If you're 1 standard deviation above the mean, you're 1 standard deviation 50 points above 100. You're at 150. And the same thing would work with 50. All right, 50 would be 1 standard deviation below the mean, and you can check by the math here. 50 minus 100 is minus 50 divided by 50 gives you a minus 1. Now what this means is that if you take any set of scores that are centered at a particular mean with a particular standard deviation and convert that entire set of scores into z-scores, you get a distribution that looks like this. It's centered at 0 and goes out by units of 1, 2, 3. This is what we call the standard. Even though it says in that little header up there, the normal distribution, this is not only, this is the normal distribution, right? Because, I mean, there are infinitely many normal distributions. Take any mean, any standard deviation, you can get a normal distribution around it. But this is the normal distribution. This is the standard normal distribution. You might remember from my stats class a very well-loved 4-sheet piece of paper that had a bunch of numbers on it. There's a bunch of those, right? But there was one that was 4 sheets with staple with all kinds of marks because that was our standard normal table. That thing gave us probabilities associated with particular scores in this distribution. You might have wondered, how can we do, Dr. Falkenberry, how can we do all of these computations when the normal distribution that I'm going to get for my research project is going to depend on what my scores are? You know, my scores are all centered at 20 with a standard deviation of 5. Well, my scores are all centered at 100 with a standard deviation of 10. How can we do computations with those? And the answer is simple. The answer is convert them to z-scores. And if you convert them to z-scores, your distribution that's centered at 20 and your distribution that's centered at 100 will all be centered at 0. And so we can do all of our computations on this standard normal distribution.
You want to hear a nerdy example of that?
Yeah.
When I was doing my my internship for psychology, the person I was going to have as a roommate, she went online and did all this research on apartments and converted everything to z-scores. Like all of these measures, square footage, number of bedrooms, price per month, all of these things, she converted it all to z-scores, and that's how we chose our apartment.
That is awesome.
Yep.
Yes.
So you can use practical application. You can use this.
My friends, that is a goal for you as you are transitioning to graduate school. You really need to do that. I promise you, we will all write you good letters of recommendation if we find out that you're doing that. That's good stuff. I like it. So this leads kind of to the transition between using statistics as a descriptive tool to now using descriptives as an inference tool, as a way to make judgments about how likely am I to get a certain result. Right? The standard normal distribution is a good vehicle for this because the standard normal distribution has a very predictable pattern to it. For example, you see something up here written as the 50, 34, 14 rule. What is that? What that is a simple, sometimes it's called the empirical rule, but it's a simple eyeball estimate to tell you proportions of the normal curve, the normal distribution, that are within certain predefined sections. Okay? So for example, the 50 part of this rule refers to the fact that exactly 50% of the data is beyond the mean, is beyond a z-score of 0. All right? Exactly half the curve is right here on the right side of the mean. Now, because the normal distribution is symmetric, I can say exactly the same thing for what's going on the left side. All right? So I'm only going to make my drawings on the right side, but it also applies to the left side. So the 50 part means all of that from the mean, right in the middle of it, all the way into this tail, which goes on infinitely, by the way. It just gets smaller and smaller and smaller to where you can't even see the difference between it and 0. That's all 50%. Now the other sections have some nicely defined parts as well. This part between 0 and 1, between the mean and 1 standard deviation above the mean, turns out to be about 34%. It's a little closer approximation would be 34.13%. But again, this is an eyeball estimate. So about 34% of the data is in this little sector between the mean and 1 standard deviation above the mean. Now using symmetry, that means that this sector has about 34% in it, which means between -1 and 1, between 1 standard deviation below and 1 standard deviation above the mean is about how much of the curve? 68%, and that's how you'll often see this presented as well. Keep going. This one turns out the between 1 and 2 standard deviations, it's a little over 13.5%. If you just round it up to 14, that again will give you a good estimate. This is about 14% of the curve here, which means about 14% of the curve here. By the time you add these up, you get something really close to 95%. Okay, and then that means you've got 2.5% left in each one of these tails. So again, the normal distribution gives you nicely defined, there's probabilities that you can remember very easily. Yes, sir?
Does the curve have to make the assumption that the population is symmetrical?
Well, this is assuming that we are dealing with a normal distribution. So yes, if you are dealing with a normal distribution, then that assumption is included because the normal distribution is by definition symmetrical.
So what happens if the population is not symmetrical?
Good question, because populations are rarely that nice, right? I think I might answer your question in a second. If it's not on a slide, I'll answer your question. All right? It's a clever little answer to a very good question. What happens when the population is not normal? All right. We've already said this, so I'm just going to go on. 68% of the scores are within 1 standard deviation of the mean. 95% are within 2 standard deviations of the mean. Okay. Yeah, hang on just 1 second. I want to see. Yeah, I'm not going to do this. Let me go ahead and answer your question now. Okay. I wasn't sure if I got into this technicality. So the question was, what happens when the population is not symmetrical or not normal? Because it's pretty easy to believe that that would not be the case for all underlying distributions. In fact, active area of my research lab is dealing with population distributions that are not normal. Right? So are there problems with that? Turns out that what you guys do when you do research, when you take samples of individuals and collect and compute the sample mean, what you're interested in as a distribution is not the original population anymore. What you're interested in is the distribution of sample means that you would take from that population. And there's a little thing in mathematics called the central limit theorem, which says that if you take any population, so it could be, we'll just use a little marker here. Here's a population for you that certainly is not symmetrical. Let's say your population looks like that it's bimodal, has a couple of distinct humps in it. And you take samples from that. So you take a sample of, say, size 30, because 30 is a good number, why not? Take a sample of size 30, write down the sample mean, collect it down here. Take another sample of size 30, write down the sample mean. And you look at how all those sample means stack up. Because you used a big enough sample, say 30, your sampling distribution looks like this. Turns out that even though your population itself was not normal, the distribution of sample means is normal. And because that's what we're interested in when we take samples, as you'll see when we talk about our inferential statistics, that alleviates the concern about the original population, which is certainly not normal. Does that help?
Yes.
Yeah. If you don't believe me, I'll give you a proof of the central limit theorem, but we'll do that later. So it works out that way. It's kind of nice. There's actually some really good web outlets that demonstrate this. You can literally use your mouse and draw the nastiest looking population distribution, and you just watch the samples pile up, and I'll be darned. I mean, it gets me every time, and I know the mathematics behind this. It just turns out to be this nice, normal thing. It's like magic, right? It's like God interfered with statistics just for that. Anyway. All right. So, inferential statistics, we've got these samples, right? We can describe them in terms of z-scores so that now everyone can talk about everything from a standardized standpoint. What is it that we do with it? Well, remember, the purpose of doing research is to be able to make claims about populations based on data collected from samples. So here's kind of a standard paradigm. I use memory because it's one of my favorite things to teach. So here's an example experiment. You have participants in 2 groups. Group A gets a treatment to improve memory. Maybe it's like, drinking tea or something like that. I don't know. It's some sort of memory improvement procedure. Group B gets no treatment. There's some sort of control group. By the way, what kind of design is this called? Ooh, pop quiz. Starts with a B. Ends with between subjects. This is a between subjects design. This is an independent groups design, if you want to call it that. Yeah. So this will tell you something about stats you want to run later. After the treatment period, both groups get tested on a memory test, and you find out the following. You find out that Group A gets a memory score of 80%. Woohoo! Group B gets a memory score of 76%. Woohoo! So here's the question. Group A improved by 4 points. So what? Is that a real difference? Did I reliably increase everyone's memory? Or is it just the case that those groups had a different memory score just because of sampling error? Right? The idea of measurement error, I got a weird sample, something like that. So I have to ask myself, are these differences that I observe statistically different? Okay? And that's the point of hypothesis testing. Remember your favorite hypothesis testing. It's one of my favorite things to teach, even though I absolutely detest the logic of it. I love inflicting it upon undergraduates. So here's kind of how it goes, right? If you've had me in face-to-face, actually, if you've even had me in the online course, you've probably seen me do this on your computer. So a hypothesis test is the ultimate sort of double negative logic. Let's walk through the tests, and then I'll give you my sort of quick and dirty way of doing this. First is you state your hypotheses. We're going to go walk through each of these. Then you set a decision criteria, you collect some data, you compute a test statistic, and then in the end you make a decision. You make a decision about your null hypothesis. You either reject the null or you fail to reject the null. Okay? Let's talk about what all this means. Step one, you want to state your hypotheses. In hypothesis testing, the way we do it in this discipline, we usually set up 2 hypotheses. One is the so-called null hypothesis, which is the opposite of what you're interested in. It's the opposite of what you predict. Okay? So in our case, in this memory groups, this memory treatment example, this will be something like, there are no differences between groups. Because we're actually predicting there to be a difference. So the null hypothesis would be there's no difference. This is the one that you're testing. It's not what you're interested in getting support for, but it's the one you test. The alternative hypothesis is the opposite of the null. So if the null is there are no differences between groups, the alternative hypothesis is there are differences between groups. Okay? Even though it seems like what we're doing in research is trying to prove this hypothesis, we can't. What we have to do is get evidence for that alternative by rejecting the null. What that means is you want to literally be able to say, I have evidence to suggest that there is not no effect. And please don't write that in your paper, because if you write that in your paper and I look at it, I'm going to say, okay, yeah, that's not good. But it is literally what you're doing. By rejecting a null, you're saying it is not the case that there is no effect. Right? You're negating the no effect statement, and that leaves you with support for the idea that there is an effect. But it is kind of fun to say there's not no effect. And you can literally say it, nobody will look at you strange. So in this example that we have in our memory experiment, you might say that the null is that the mean of group A is the same as the mean of group B. That's your specific operationally defined null hypothesis. And then the alternative is the mean of group A is not equal to the mean of group B. Okay. Step 2. We're going to be making a decision, right? We're going to be making a decision about whether to reject the null. So we need a criterion upon which to make that decision. When will we have enough evidence to reject the null? This is defined by something called our alpha level. This is something that you always specify in your results section. We did this test with an alpha level of 0.05. Or if you're reading some of the latest stats work and all that stuff on Twitter, you might even be setting it down to 0.005. But the alpha level is your guide for when to reject the null. Based on that alpha level, based on your decision, there are two different ways to go wrong here. Okay? Because you're making a decision, you're either going to be correct or incorrect. but it's two different ways for you to be correct or incorrect. What do I mean by that? Well, let's look at what the possibilities are. Essentially, what you're doing is you're pitting your human sort of experimenter decisions, either rejecting the null or fail to reject the null, against some objective real-world truth. Either the null is the correct hypothesis, that is, there's no effect, or that the null is wrong, that there is an effect. So when you pit two possible decisions against two possible truths, you have two different ways to be right and two different ways to be wrong. The ways you're right, of course, are signified with happy faces here. Let's look at those. If you reject the null and the null was wrong, that's good. That's the correct decision, right? Likewise, if you fail to reject the null when the null is correct, you don't want to reject it. So that's a correct decision. So those are good. Where does it go wrong? We'll start up here first. Suppose the null is correct. Suppose there's really no effect of this memory treatment, and you reject the null. Well, that's an error. You've rejected a null. You said there's not no effect. Well, there really is no effect. So that's an error. That's called a type 1 error. It's also called a false positive. You don't want to do that, all right? You don't want to make type 1 errors because then you're saying there are effects when there really aren't. And then you start selling people this memory treatment and it's really nothing. So you don't want to make type 1 errors. The other kind of error is this one down here. Suppose the null is wrong. Suppose there really is an effect. There really is a difference, but you fail to reject the null. You didn't find it. In that case, you make what's called a type 2 error. And this is a false negative. You're saying there's no effect. Well, is there really no effect, or did you just not find it? So it's a different kind of error. So definitely one of those things you want to keep thinking about as you're preparing for your major field achievement test is that type 1 versus type 2 error. That is a big sort of fundamental thing in the field, regardless of specifically the stats you run, that sort of thing. These are errors that plague all research-based decisions. So in the end, what you want to be able to do is control those errors. Yes, sir?
Is a type 2 error a sample size error?
Can be. Can be. Yeah. There's many possible reasons for a type 2 error. Sample size is one of the most common. So when you say, I could be making a type 2 error, you might be saying something about, I don't have enough power to detect this effect. How can you get increased power? Increased sample size is one of them. It's not necessarily the only way to make a type 2 error, but sample size is certainly a big deal when you're thinking about type 2 errors.
Can I do an example, a
Please.
real world example?
Please.
Okay. How many of you are familiar with the Andrew Wakefield study on the MMR vaccination and autism spectrum disorder? You heard of this, right? So Andrew Wakefield published in The Lancet that the MMR vaccination was tied to increased autism rates, okay? Subsequent population level studies, epidemiological studies have negated that effect. So what type of error did Andrew Wakefield make in his Lancet article?
Type 1.
Correct.
Ooh,
Yes.
Good job.
What is
Good
it, the
job.
pregnancy and the man is pregnant?
Yeah, there's that little meme going around. It's like from a stats book or something, a little meme going around on Facebook right now. So there's a picture of a lady who is just very obviously pregnant, and there's a doctor standing there and says, nope, sorry, you're not pregnant. And then there's the other one that is, there's a man standing there, and there's a doctor saying, yep, you're pregnant. One of those is a type 1 error. One of those is a type 2 error. I'll leave it to you to figure out which one's which. Okay. Since we have these two different types of errors, we want to make sure that we can control them. So in the slides that have been made available to you, there are some indications about how you can do this with type 1 and type 2 error rates. Type 1 error, just to keep moving here, type 1 error is controlled by your alpha level. That's why we use that standard 0.05. We can live with a type 1 error rate of 5% is what we say when we reject things at the 0.05 level. Type 2 error, this is related to something called statistical power. Basically, the idea is you want to have enough power in your experiment to detect the effect if it's really there. And so you minimize type 2 error by maximizing power. They're inversely related. All right? Step 4, you compute your test statistics, and so, I hope you guys aren't going to be doing this by hand. Hopefully, by the time you've gotten to this, you've learned to use some computer software, be it JASP for my courses or SPSS if you took someone else, something that you can use to compute some test statistics. And then you make a decision based on those tests to either reject the null, in which case we interpret that as a statistically significant difference, or fail to reject the null, where we say there was no statistically significant difference. Notice I keep saying fail to reject. I do not say accept the null. Remember, we cannot have evidence for the null unless you are a Bayesian. It's a different course. So what is this whole statistical significance thing? When you reject the null, all right, when you get this output on the stats program that makes you think, oh, I reject the null, what are you doing? What you are doing is you are saying that the observed difference, the difference you're seeing in your data, is above what you would expect by chance alone. Okay? Remember, beyond that sort of noise threshold, the 4% that we saw in the memory example, is that real or is that just sampling error? And so the idea is that what do we mean by chance? What we mean by chance is that sampling error. It's that notion of how big the sampling distribution is. And there are all kinds of things that affect this. Sample size affects the sampling error. The bigger your sample size, the lower your sampling error. So use bigger samples if possible. Another way to say this is if you have a sample of size 4, you're going to have a lot of potential sampling error. Okay? So use as big a sample as you possibly can. And also population variability goes into it. If there's just a lot of variability in the population, there's going to be a lot of sampling error as well. It also means that there is a probability of 5% that you have made a type 1 error. Okay? That's the part we don't like to think about. But when you say, oh, I've got a statistically significant result, p equals 0.04, it's less than 0.05, so it's statistically significant, but there's also a 4% chance, or possibly greater, that you have made a type 1 error. So you have to keep the interpretation of your results within that sort of lens, right? Don't think you've cured cancer with a p equals 0.04. And I also mentioned that statistical significance is not the same thing as theoretical significance. You can have statistically significant differences that are obvious, right? There's an obvious difference in the height and weight of males versus females. Is that theoretically meaningful? It doesn't tell us anything new, right? So doing a study to say, well, I'm going to take a sample of males and a sample of females, and I'm going to record their heights and weights, and I'm going to show they're statistically significant. So what? Right? Statistical significance doesn't mean anything beyond what the theory tells you. So make sure that whatever you're doing is grounded in theory. And I've already mentioned this, but remember, you cannot accept the null hypothesis. And you should also check to see if you've made a type 2 error. You should try to guarantee through some means. It could be, I've thought about the sample size and this seems big enough based on past studies. That's sort of a minimal level. Or you can go full out and figure out how to do a power calculation. To do that, I think you'll probably do all right in the course. So what I want to now transition to, we're kind of on the home stretch of the review today, is I want to talk about statistical tests. And this is not going to be a lecture on here's how you do a t-test and here's how you do an ANOVA. You've done that, guys. You've done that in your stats and your research courses, both textbook in stats as well as applied through the labs and research. So I know you've done this before. What I want to remind you of is why. What is the point of all of those tests that we do? Well, remember, the idea is with a statistical test, we want to be able to make a decision about whether our difference is real or just due to sampling error. To do that, we've got to be able to analyze all of the variability that we would expect between our different groups. So again, I'm still using that memory example, the group A that had the memory treatment and the group B that was the control. I'm still using that as sort of my background here. And so now I've got two potentially different populations with different sources of variability. So if I start to kind of quantify, just start writing down on the back of a napkin, okay, where could the error come from? Where could the variability come from? So I could have, of course, variability that's due to random sampling error. Again, we're pulling samples. This is ideally a random sample of individuals, and so there's just going to be variation in how they perform naturally. Right? Right? We call that ER for error. There's going to be individual differences. We'll call that ID. And then, of course, there's going to be variance that is due to the effect of a treatment. That's actually what we're interested in, right? So there's all kinds of variability. Some of it's good, like the bottom one here. We want to detect that. Some of it's bad. I mean, we want to minimize that stuff as much as possible. So how do we do that? How do we quantify those things? Well, what we do is essentially we develop a test statistic. So this could be a z-score. It's a great test statistic. Could be a t-score. Does anyone remember what the difference between a z-test and a t-test is? I mean, I know they're different letters. But I mean, why would you use a t-test? Why do we use t-tests all the time instead of z-tests? That's a hard question here. It's a subtle difference. The difference is the following. If you know the population variance, so you're dealing with a normed test like an IQ test or some sort of standardized test, then you use a z-test because you know the population variance. If you don't know the population variance, which is the case for most research that we do when we're just measuring things and we have to estimate the population variance from our sample, turns out the z-test is woefully bad and you have to do something slightly different. And that's where the t-test comes from. Other than that, they're the same. But the difference is in whether you know the population variance or whether you're having to estimate it. If you have to estimate it, you're using a t-test. So whether you're using a z-test, or a t-test, or an ANOVA, or a chi-square, or a binomial test, or any other myriad tests that could be out there, what you're doing boils down to this equation up here. You're wanting something that indexes the observed difference, what you're interested in, divided by the difference you would expect due to chance. So the idea here is the bigger this fraction, the bigger this number, the bigger the observed difference is relative to the sampling error. Okay? In other words, the bigger this good blue thing is right here. Right? The bigger this treatment effect is. So when you have a really big t-score or a really big f-score in ANOVA, that's telling you that your observed difference is way beyond what you would expect by chance. And that's why big test statistics are a good thing. When you see something like that, that big thing reflects the fact that, I mean, these are all the same source, so the difference has to come from the treatment itself. That's the only thing left that could be changing here. So to reject the null, you want that test statistic to be big. You want it to be large enough. What do we mean by large enough? Well, we mean beyond the sort of rejection levels that alpha dictates. So alpha determines where on your distribution your boundary is before you would reject or fail to reject. So let's say you got them right here. A typical thing would be a z-test where the boundaries are plus or minus 1.96. If your z-score is beyond 1.96 or beyond negative 1.96, you would reject the null. If they're not, then you fail to reject the null. The decision becomes that simple. Oops. So that's it. No matter whether you're doing a z-score, a z-test, a t-test, an ANOVA, a chi-squared, whatever, it comes down to that game. The reason we do hypothesis testing in this discipline, and in many other disciplines. By the way, most hypothesis tests that you deal with actually started in agriculture. Right? It's kind of cool that way. Sir Ronald Fisher was an agronomist, and he invented the ANOVA. I've already mentioned these, but again, this might give you some indication of what kind of test you'll be doing. You're not going to be doing a whole bunch of tests on your capstone projects, but there will probably be one good one that you'll do, and it will depend on the design. So there's all kinds of flow charts available. The textbook that I use for research, the McBride textbook, has a great flow chart in it. Right. I think Dr. Robertson probably has one from that textbook that she'll give to you guys or has already given to you guys. So you kind of follow this flow chart and you figure out, okay, what is my design? Whatever my design is going to define what my test is. Remember at the very beginning, before we started this, I said you've got to know what your question is. If you know what your question is, it's easy to figure out how to analyze it. If you don't know what your question is, it's really hard. Just to tell you right now. And then don't come in here when it's 2 days before your poster presentation and knock on my door and say, will you help me look at my data? Because I'm going to ask you, what's your question? And if you say, I don't know, I can't help you. It's not because I don't want to help you. It's because I don't know how to make sense out of all this data. The only way you can make sense out of data is to frame it within the confines of questions. Know your question. Know your question. Have I beat them over the head about that?
I think so.
Okay, good.
Do y'all know your question?
If not, you're going to know your question? Yeah, that's what's key. So if your design boils down to you've got a single independent variable with 2 groups, that's many of you are going to be having. That's a good, simple, very straightforward, meaningful. I mean, when we teach science to 3rd graders, this is the design we use, right? It's not to say what you're doing is elementary. It's to me, it's fundamental, right? It's the basic idea of an experiment. You got one group versus another, and they're different things, right? So if it's between subjects, what would you do? You do an independent samples t-test. Why? Because you do. Because it works. It does what you want it to do. It determines if there's a significant difference between the group means. If it's a within subject design, now some of you might be doing, say, I don't know, something from this awesome psycholinguistics course that you took this summer or something. You might be doing some sort of semantic priming thing. So you got people reading sentences that are of one type and sentences that are of another type, and you want to compare the mean reading times of those sentences. Well, that's a within subject design, right? Because every participant participates in multiple conditions. So in that case, you would use a paired samples t-test instead of an independent samples t-test. Well, Dr. Falkenberry, couldn't you use one or the other? No. Right? They don't work if you don't use the right test. You'll get meaningless garbage as output. So you've got to know what your design is. If you are one of those souls that says, well, I want to compare 5 different groups on this measure. Good luck with that. You're going to use an ANOVA because you got to have some tool that will let you analyze group differences in more than when there are more than 2 levels. So then you'd use an ANOVA. Is it going to be between subjects or repeated measures? Depends on your design. Depends on your question. Some of you guys are going to be having a single independent variable with a categorical dependent variable. All right, so you got this independent variable, you got this group versus this group, and then you want to look at choices that they make. Right? I choose this soda versus this soda. I don't know, maybe you're looking at the effects of, let's come up with something silly here. The effects of the Sonic drink that was offered on this thing that they chose. I don't know. In that case, you're not measuring a continuous variable, you're measuring a categorical variable. There's a chi-squared test. So again, what your question is what defines your test. Non-experimental designs. Just real quickly, if for no other reason than to remind you of these before your major field achievement test. Experiments is what I do, all right? That sounds like bad grammar, but I call experiments a single noun, right? Experiments. That's a singular noun for me. That is what I do. I am an experimental psychologist. What that means is we have at our fundamental core random assignment. And that's important because what that random assignment does is average out all the individual variation that you don't care about. So if one more person asks me, well, you think males or females are going to do different on this math test? I don't care. First of all, there's not any difference in them. And second, even if I did care, they would be averaged out because that's not what I'm manipulating. It's all about doing that random assignment. But sometimes you can't perform a fully controlled experiment, either because the issue of interest doesn't let you do that, there are limited resources. These kinds of situations call for a non-experimental design.
So you have like a 1 semester time frame to do your study.
Yeah, exactly, right? Yeah, exactly. Of course, I would argue that's perfect for a little experiment as opposed to one of these longer things, which takes much more effort. But I mean, these come down to surveys, doing correlational designs, or the 3 that I'm going to remind you of, quasi-experiments, developmental designs, and small N designs. By the way, please don't do developmental designs for your capstone project. That would not be a good idea. What is a quasi-experiment? It's an experiment, but almost. All right? It's quasi in the sense that it looks just like an experiment, and it tastes like an experiment, but it doesn't have random assignment. So it might be something like smokers versus non-smokers. Can you randomly assign people to a smoking group? You can, but good luck with that. All right, it just doesn't work that way, right? You kind of have to work with the individuals as they come to you, and so there you've already lost the element of random assignment. You might be interested in subject variables like high versus low IQ. Again, you can't randomly assign someone to one of those groups. You can't randomly assign someone to be a male or a female for the day. And so there are many different types of times when you cannot do a random assignment. In that case, you call it a quasi-experiment and move on. If that's the case, a lot of times what we do with quasi-experiments is some modification of the pre-test, post-test design. That's a very common quasi-experiment. This is very simple design where you measure a behavior twice, once before some treatment and once after, and the thing you're looking for, the thing you're doing a test on is there a difference between pre and post? There are some problems with this. There are history effects, there are maturation effects. These are things that you've talked about in research before. So how do you get rid of those? Well, you could have a pre-test, post-test design with non-equivalent groups. You could have one group that has a treatment, one group that doesn't have the treatment, but you still measure them in pre and post. So that might help you get rid of history effects and maturation effects. But it doesn't help you get rid of the testing effect, which is the idea that just being exposed to the test causes a different behavior at the end than the control group. So how would you do that? It's even more complicated. Right? And so there's something called a Solomon four-group design that I love talking about in research class, but I'll let you go back and look at the notes for that. So the idea is, even though these are non-experimental designs, when they're done right, they're just as effortful as experimental designs. Good research takes effort, regardless of the design. That is a very important thing to consider when you're doing research. Why did I say you don't want to do developmental designs? Well, because these are the ones that require a lot of time, usually. Okay, so the idea with a developmental design is that age is your independent variable. Technically, it's a quasi-independent variable because you can't randomly assign people to be 3 years old or 5 years old. Okay, so it's a quasi-independent variable. I said 3 major types and I've only listed 2. That's because I cut off one of them. I just didn't want to talk about the anyway. But we will talk about cross-sectional longitudinal designs. Cross-sectional designs, you actually could do a cross-sectional design here, but good luck getting the IRB approval for it. Wouldn't recommend that. The idea with a cross-sectional design is you take a bunch of different ages at the same time. So you study a bunch of 4-year-olds, and then a bunch of 7-year-olds, and a bunch of 11-year-olds right now. And so you see if there are differences between them, but you're not following the 4-year-olds all the way until they're 7, and all the way until they're 11. You're looking at differences between these groups. On the other hand, a longitudinal design, you actually follow them. So you take them at age 11, and then on to age 15, and then on to age 20. As you can see, this is going to be a 10-year study. Okay? So don't do that for your thesis. And the big difference, I don't know if you caught this or not, if you think about between versus within subjects, that's what defines the difference between a longitudinal and a cross-sectional design. In a cross-sectional design, age is a between subjects variable. You're in one age group only. On the other hand, a longitudinal design, age is within subjects. You are tested at this age, and then later at this age, and then later at this age. And then finally, small N designs. Okay? These are the ones where you have very small samples, but you do a lot of trials on them. You look for behaviors within that participant. These are very common in some areas. Psychophysics is one of them. Clinical settings. Studies and expertise. If you've had me for learning, we've talked about people learning how to play chess and people learning how to increase their working memory capacity. These weren't large studies; they were like case studies almost. But there was a lot of trials within that one participant. I'll just say one of the common ones is the ABA design. This is used in behavioral studies a lot of times. You look at a baseline behavior, we call that an A phase, and then you give some sort of treatment, which then may change the behavior. Well, don't stop there, because it could have been something else that came along at the same time that caused that new behavior to happen. And so to infer causality between the treatment and the behavior, you want to then remove the treatment, and if the behavior drops back down to baseline, you've got a nice little reversal phase, and that reversal phase can tell you something about causality. I don't know much about small little designs. I don't do those, but that's the basic idea on those ADA designs. And of course, there are advantages and disadvantages. Yeah, this is all included in your notes, and this is what happens when you try to cram an entire year's worth of course material into one lecture. But I think that covers it. The big ideas are what you need to remember, and of course, also remember when you're doing research, you got to know what your question is. That makes things so much easier. So with that, I think we actually have still quite a bit of time left that we can talk about specific questions that you might have.
Excellent. Good.
Yeah.
See that you all prepared your questions. Okay, good. Yay.
Yes, Lindsay.
So I'm doing a whether or not someone is diagnosed with an anxiety and their scores on the BAI. I also wanted to do whether or not they are in college. Would I do two separate independent T-tests?
Okay. What is the BAI?
Like anxiety and
Okay. So you've got one independent variable of diagnosis, and then you've got another possible independent variable of college student versus non-college student.
Yeah.
So there's a couple options here. You can do two separate, but these are going to be between subjects, right? Because you either have anxiety or not, or you've either been diagnosed with anxiety disorder or not, and you're either a college student or not. So in that case, that would be an independent samples T-test. I'm assuming that the BAI is a continuous scale, like you don't just like get a category. Okay, in that case, you've got perfectly set up to do an independent samples T-test. Another possibility is you could cross those two independent variables, okay? And so what I mean by that, let's see if I can draw a picture with this marker. So let's say low diagnosis and then high diagnosis. I am just talking about this from the experimental design standpoint because I know nothing about any of this, but what if you could then cross that with college versus no college? Okay, so that you had participants in each condition. So you had college students with low diagnosis, college students with high diagnosis, and no college students, or not students anymore, but no college folks with low and no college folks with high. In this case, you would have a 2x2 factorial design. And that might be interesting because then you have one more thing you can look for. So with the one before, you have the possibility of there being differences due to diagnosis. That's one test. And differences due to college experience. Okay? What the factorial design would let you get is both of those, we call them main effects in that, plus is there an interaction between the two? Right? Does being in college versus no college affect the pattern that diagnosis plays in that BAI score? Right? Maybe if you're a college student, maybe you get something like this. I'll just give you an example of what some data might look like here. Let's just put some numbers in here. I think it'll be easier. So it could be the case that the effect is 30 versus 60 for college students. Okay. I don't even know if that's on the scale, but let's just say that it is. But if you're not in college, it doesn't make a bit of difference. Okay. So that would be a pattern that you would not capture with the two independent samples T-tests by themselves, but you can capture this as an interaction effect. Now, making sense out of the interaction is the next step, but from a purely statistical point of view, that would be the advantage of a factorial design.
Because I remember doing all this. I just don't remember how.
That's the beauty part of knowing what your question is early, because then you can go back and look at your old labs, or you can knock on an old professor's door and say, can you remind me how I should structure this data? And then you do, and then when you collect your data and it's time to run the test, it takes 5 minutes.
Yeah.
Literally the time it takes to open your software and open the data file. Then you click something. So, yeah, the thing about data analysis is the hard work is always in the planning. The data analysis itself should be simple. If not, you didn't plan well. Not everybody shared my opinion on that, but that's okay.
I'm all about planning. I plan my planning.
Meta planning. Good, great question. Great question. Other questions, guys?
Okay, I'm gonna throw mine out there.
Please.
I'm clueless, honestly, because I don't ever overthink anything.
Never. Never.
Okay,
You said it, Amy.
I know, because I'm becoming more and more aware of doing that. Nothing's ever simple. Okay, so, because I'm old and I have like these hardcore interests, I have trouble pulling away from them, so I really want to do my study on something with, thank you, the autism and college. And I have a great resource of adults that are high functioning autistics. I can't use Asperger's anymore, but they're all Aspies on a chat board. Hundreds of people. So that's awesome. I'm trying to figure out how to form my question, because what I want to look at is people that went to college or tried and failed out of college. Is it because of lack of support? Did they get support? And I know, I'm like digging into something that is like multivariable to the extreme, but how do I pare that down? And is there something that,
Focus on that right there. So I'm not saying this is what you should do, but for
Yeah.
example, I just heard a research question in what you just said.
You did?
Uh-huh. You have high functioning autistic versus some other group, and you want to measure their level of perceived support.
Okay.
Now, you got to find the right yardstick to measure level of perceived support,
Right.
but I can't imagine that in the hundreds of thousands of articles in our discipline alone that someone hasn't constructed a scale, even a paper pencil scale or something you could administer to chat board people that measures level of perceived support.
You can go to the psych test thingy,
Yeah.
but you just have to be very careful about how you phrase it and what you do. Because BAI is very popular, but it was actually difficult to find it under the psych test. Finally did it.
It wouldn't be a cross-sectional like that, though.
Well, this is not cross-sectional, this is factorial.
Okay, so,
Maybe, maybe not.
because, I'm still in the beginning of your research while I'm doing this. So I'm learning as we go,
Yeah,
which is cool.
we tell people about that.
It's cool,
You know that.
because it works.
Yeah.
But,
Would she have to do that?
No. See, here's the thing, and this is why I often don't like to give an example of
Right.
what you should do, of what a person could do, because then everyone's like, okay, now how do I fit what I want to do to that? Because there's a solution. But that doesn't mean that that's the best way to study what you're interested in.
but it would be a within subjects. Well, no, it wouldn't, because I'm taking two different.
Yeah. So what you've described to me so far is between.
Would be between, and then,
It's only within subjects if you have people doing multiple experimental conditions.
right, which really wouldn't be possible.
If you're doing cognitive stuff, you're going to be dealing with within subjects, just by the
Right.
nature of it, right? But a lot of these individual difference type studies, that by its very nature is between subjects.
Well, and what you've talked about too is your entire if you did your entire population of people from these boards that are Aspies, right? And then you divided them into college persist and non-college persist, and then you measure level of support,
Oh.
right? Then you've got your variables.
Yep. In fact, in a perfect little factorial design.
You can actually knock out the variable of the autism.
Yeah. Then you would have college persist or non-college persist, and that would be your
So
category.
that's what I really, really, really want to look at,
Mhm.
is, are we not going to college because we just don't want you, can't do it, whatever, or are we not going to college because the supports are not the correct supports? That's what I want.
And that's what you should do.
Then I've got some folks in here who are looking at class category, right? Freshman, sophomore, junior, senior, right? And so in that, you're going to be looking at a different statistical analysis, right?
Who wants to ask that question?
I'm doing motivation, like it increases as college students go up. Like,
In classification?
Yeah.
Okay.
So,
So essentially, I think it helps to think, what could my results look like, right? So when you said that, my immediate thought was, I bet, I'm assuming that you want to have an ordinal variable of freshman, sophomore, junior, senior. By the way, what makes it ordinal versus nominal?
There's an order.
It's the best named thing ever, right? Ordinal, right? So you want to see if, what was that dependent variable you mentioned?
The
Motivation?
motivation.
Motivation, you want to see if it does that. Okay, cool. So there's a couple of ways you could do that. One is you could, I'm thinking and talking at the same time. One is you could do a linear regression, right? And so you could use motivation as the outcome variable and classification as the predictor variable. In that case, what you would get out is two things. You would get an intercept. It's like literally where it starts, right? It's probably not going to be meaningful in this case because what's before freshman? Yeah, it's all kinds of stuff, right? But the big thing you would get is slope, right? It's literally how does it increase as you go up by each one. And you would also be able to test whether it's a significant increase.
What is that one?
Linear regression.
Oh, it would make my heart so happy to see a linear regression in one of these presentations.
Exactly.
Ooh.
And this one's like set up perfectly for that.
Yeah.
And again, JASP, what I teach you guys in my research class, does this perfectly. Another thing that you could do, it's a little more sophisticated, but it would be awesome, is an ANOVA, right? Because it's more than two groups. But you would do an ANOVA and then you would test what's called a contrast. Is there a linear contrast? Is there a linear pattern? Because the ANOVA by itself just tells you there are differences. It's about the most useless output ever, right? There are differences. Where are they? You have to do more, right? You have to test like a contrast. And so it'd be an ANOVA with a linear contrast, which turns out is the same as linear regression. Yeah. But it sounds cool when you do
And
it.
I was wondering if I have to look at interest. I was thinking interest level was gonna like kind of be with motivation
Mhm.
because if you're interested in something, you're gonna be more motivated to
Right.
do it.
Right.
So do I have to like add that to it, or is that
Well,
something that will-
I'm gonna give you a thought argument here. Argument. I'm a thought leader today, apparently. If so, wouldn't you also need to add hair color and eye color? You see where I'm going?
Yeah.
At some point, you just measure what you're interested in and let the other things just be random error. And then you hope that the effect of classification is enough to override all that random error.
Well, the purpose of this is more to get people back on track on like what they really want to do. So like if you're or like a junior and you're still not motivated in your classes to actually get past that point, obviously you need to maybe.
So what if you did this with low interest individuals versus high interest individuals? And then you compared the slopes that you got on those. I mean, that would be very, very sophisticated. Yeah,
That'd be fun to do.
exactly, and easy. If you wanted like a comparison of the interest variable. Yeah,
Your sample would need to be pretty big.
Mm-hmm.
yeah, that's the only issue.
Yeah.
That's the part.
Right, which is going to be hard.
Yeah.
What else?
But again, I know for me, when I'm evaluating these projects, when they get done here, it's process
Yes.
that I'm looking at more than outcome. If you don't get a significant effect, you're okay. It could be because you just didn't have enough sampling. Okay. But oh my God, you just did a linear regression on two different groups and compared the slopes. That's awesome. That's kind of what
This
we're
is
looking at.
crazy because like in your class, I was so stressed because I didn't
I do that too.
I missed one day and I lost, and so my friend helped me a lot in that class. But now like it seems fun, like to me, like that seems like I know how to
You're on
do
the
that
other
because
side of it.
yeah, and so I'm like,
Yeah.
okay, I'm just plugging stuff.
Exactly. That's why I do research. I play every day.
So,
Carissa. Oh, okay, I didn't know who did first there. Go ahead.
During mine was like personality, anxiety, we say like between extrovert and introvert, and so like one of those personalities has more anxiety. I don't really know how it works,
Mhm.
but I'm just kind of looking at, I think I'll have to do like the test, like the Myers-Briggs test, and then do anxiety. I don't know.
Oh, this is a great question, right? Oh, good. I'm glad we have time to. We have what, 3 minutes?
Yep.
Okay. So you've got an issue because you're giving multiple measurements to participants. This is for every one of you guys because I sense that this is going to happen. You're going to be giving multiple measurements. Is it the case that, let's say that Carissa decides to give the Myers-Briggs first, or the Big Five, which is free. So, but whichever one you decide to do, if you do it first, is that going to have an effect on the subsequent measurements of the BAI? And if the answer is anywhere in the realm of maybe, then you need to make sure and take care of that. How do you do that?
You do have, yeah.
Yeah, it starts with a C and ends with counterbalanced. There you go. Yeah, it's counterbalancing, right? Half your participants get the Myers-Briggs first, and then get the BAI. The other half of participants get the BAI first, and then the Myers-Briggs. And that way, if there are order effects, which there probably are, fatigue being one of them, those effects are averaged out. And now what you're seeing is the scores on those things.
So I would just have like one group do one and the other because so much stuff like
Well, it depends on how you're defining group. But if you, let's say you've got 100 participants, 50 of them need to do it in one order, and 50 of them need to do it in the other order.
I mean, you're gonna have to construct your measure in two different ways. You're gonna have one that has your BAI first, and then your Big Five, and one that has your Big Five, and then your BAI, and then you're gonna have to administer them to two different groups.
Yeah.
Do you think Google makes it possible for you to switch the order of what you do first?
2 different forms.
You could do two different forms. I don't know if Google may be smart enough to do two separate forms and then to randomly follow the link back. But if it is, I don't know about that. If it were me doing it, I would create two separate forms and I would send it out to two different.
Guys, what I do in the lab is I literally build 2 different scripts. Like on some things I want true on this hand, false on this hand, and I want to flip it for every other participant. I literally have 2 different scripts, and my lab assistant knows on this, for this time, let's do this one. For this time, let's do this one. It's like literally having 2 different forms.
Yeah, we were just talking about posting it on Facebook and letting random people do it. In that case, you would be able to.
Yeah, but you could do it. I mean, you could advertise it to do different groups.
Yeah.
Like you could do Twitter to one and Facebook to another,
or
or
if I should just do that because I have like.
Address the possibility of a confound there.
Yeah.
Because you're not now, you've now got you've got a variable that's correlated with your independent variable. But, yeah. Oh, and then do a bunch of independent samples t-tests.
Okay, so don't forget to make sure you're here on Wednesday, because on Wednesday we're going to do peer review of your papers. I will hand out a rubric. I will talk to you about the rubric. You will be randomly assigned a coded paper. You're not going to know whose the paper is. You're going to grade it based on the rubric. Provide as many notes and feedback as you can on structure, on form, on everything. And then I will take those up. I will give you a grade on your feedback, and I will also give you a grade on your submission. And then I will give those back out to you. Okay? Did you have a question?
We don't need to come with our papers printed out here. You'll have those printed, or like, do you want us to print out our papers? and then-
You all submitted your papers, correct?
Yes.
I'll just print them off for you.
Okay.
Good question. Thank you. All right. Thank you so much, Dr. Falconberry.
Of course, anytime. Y'all know where my office is.